Good morning, this is lecture 44 and we are continuing with our analysis on the single stage opamp, or rather the differential amplifier, which we had just introduced. As I mentioned, the differential amplifier, as we have discussed, is actually the single stage opamp, and we will come to that in a moment. The circuit we had was the following. I had the power supply rail, and I had an active load which was made up of PMOS transistors, right? And I then had the differential amplifier itself, which was made of NMOS transistors, and all of this was biased using a current source, and we call this as I0. Okay, we'll see later as to how this current source I0 can be realized. And then to look at the various voltages. This is at a supply voltage VDD, and then we mentioned that the voltage at these two terminals itself are what is it that we saw? It was VICM, right, plus VDD by 2, and this was VICM minus VD by 2, right? This is the total voltage. This can also be written as what? This can be written as your VG0, which was the bias voltage, plus VCM plus VD by 2, and this can be written as VG0 plus VCM minus VD by 2. Alright, and as we discussed earlier, VG0 is the bias voltage, small VCM is the common mode incremental voltage. Why is what was it? How was it related to your V1 and V2? We had seen that VCM was essentially V1 plus V2 by 2, right? And small Vd was the differential mode incremental voltage. Okay, now what I am in, and where do we take the output in this particular circuit? We take the output here, right? We take the output here, and this will also have something which is a bias quantity, right, plus an incremental quantity. And in today's class we are going to calculate what is the incremental gain for the common mode, and then the incremental gain for the differential mode. Alright, so I can now title this slide. This is basically an analysis of the differential amplifier. Alright, we are going to make a few approximations in order to analyze this. You will see that I'll make some approximations which may not look very consistent, but you will have to bear with me and just follow through. At the end it may make a little more sense. Alright, so for now let me just make the following approximations. Alright, I will say that the NMOS transistors have their output impedance R0 being equal to infinite. I'll say the PMOS transistors have RP, right? I am not assuming that RP is infinite, because then calculating the gain is a little more complicated. So let's just assume that the PMOS transistors have RP. You can actually calculate everything assuming R0 is also non-infinite, and then just the expressions will be a little more messy. And the current source I0, I will assume that it is an ideal current source when I am calculating the the incremental output for the differential input, right? So this is an ideal current source for differential gain, and I will assume that it has some resistance R0, right? So this essentially means R0 is infinite, right? Where's that R0? You may have some R0 like this, right? And R0 is finite when calculating the common mode gain. Okay. Maybe I should just define what these quantities are. The differential gain AD is defined as the incremental voltage. So let me call this incremental voltage as V0. Okay, so it will be V0 divided by Vd. All right, and the common mode gain ACM is V0 divided by VCM. Okay, remember that when you're calculating, when you're doing this calculation, you set VCM is equal to 0, and here you set Vd is equal to 0. Okay, so it's basically there's a lot of detail here, but the essence of the story is the following. At the input terminal, you have a bias voltage, which is your VG0, and then you have an incremental voltage. The incremental voltage has two parts. One is the common mode incremental voltage, and the other is the differential mode incremental voltage. And in a sense, you're just doing superposition. So you're treating each one of these things separately. So as I mentioned earlier, we're not worrying about the bias circuit for now. So you forget about the bias. Then I will look at what is the gain when only VCM is present, and then I look at the gain when only Vd by 2 is present. All right, and it will become clear to you as to why the current source we approximate differently for the two cases. You will see that if I use ideally I just want to use R0 equal to infinity, because that is simple to calculate. But you will find that if I do that, I will not get a very sensible result for the common mode gain, and that is why I need to include a finite R0 while calculating the common mode gain. Okay, all right. Let's now look at the incremental gain for the differential mode signal. So I am now calculating my AD. Okay, all right. So what can I do? Let me have the circuit with me, and maybe I'll just draw it again, and then draw the incremental circuit, and then let's proceed. All right. Okay. So this is the circuit that I have. No, that's not what I have. Okay. Now I'm going to look now at the incremental picture, right? So in the incremental picture, what will happen? I have to replace each of these transistors by the corresponding incremental circuits. So let's now start first with the transistor M1. How will M1 look? So I have a current source, okay, and let me call this as GMN times some voltage. And what will its voltage be? The voltage will, the gate is at Vd by 2, sorry, right? What about the source? So that is the source, right? Then I have transistor M2. Transistor M2 will be connected in this fashion. So that is again GMN, and its gate is at minus VD by 2. Fair enough. Okay, what will happen to this current source? The current source will be open, right? So there's nothing here. So if I call this voltage as Vs, then this is going to be GMN into VD by 2 minus Vs, correct? And this guy is going to be GMN into, right? This guy would be GMN into minus VD by 2 minus Vs. All right. Now let's draw the transistors, the PMOS transistors. That's M3 and that's M4. How will the PMOS transistor look? Remember, I want to keep this as the drain. So, okay. So be careful as to how you draw it. Okay, I have two current sources, and in which direction should they point? Which direction should these current sources point? Be careful. All right, now the gate is here for this transistor. Okay, and because the current source, the incremental current source always points from drain to source, right? And that is the drain, and the drain is connected to ground. Okay, and have we missed anything? Yes, indeed, we have to connect this here. All right, and let me call this voltage as VA. So what is this current source? This is GMP into VGS, correct? This is the gate, this is the drain, and that is the source. Again, drain and source. So this is GMP into VA minus 0. This is again GMP into VA minus 0. Alright, now can you, and the output that I am looking for is here. Let me call that node VB, and I am looking for VB. Okay, have I missed something? Yes, indeed, I have missed the resistors that I wanted to add. So I have a resistor here which is RP, and I have another resistor here which is again RP. Okay, and just to be clear, my output voltage is there. All right. Okay, now how do I calculate what VB is? Okay, we can look first at this node, which is called the tail node. Okay, look at the current that is entering from here and the current entering from there. The total current has to be 0. So at the tail node, what do you have at the tail node? You will have GMN into VD by 2 minus Vs plus, that is this current, plus now I take this current which is GMN into minus VD by 2 minus Vs. Total current is 0 because no current is leaving here. So what does this show? This goes, that goes. So I essentially get the relationship that Vs is 0. Okay, very good. So if Vs is 0, I can remove this Vs from here and this Vs here, right? I can remove that Vs there and this Vs here. This simplifies matters. All right. Anything more that I can do? Look carefully. Consider this particular controlled source. If you realize the current through this control source is dependent on VA, and VA is also the voltage across the current source. So what can you do with this particular current source? You can replace this. We have done this many times. So this is essentially a resistor, and what is its value? Its value is 1 by GMP, and you can get rid of this. Alright? Alright. Now can you calculate what VB should be? In order to analyze VB, okay, before we get VB, maybe we should get what VA is, right? Alright. What is VA now? You have a current of GM into VD by 2 flowing this way, correct? And this is 0. So what is VA at node A? So VA is nothing but 0 minus GMN into VD by 2, and that is flowing through a resistor given by RP parallel 1 by GM. Alright? Very good. Okay. Now let's analyze only the we now have to analyze the situation for VB, and I can actually make a simplification there. So realize now that we found Vs to be 0, right? So this is essentially ground, and you have this current source, and then you have this other current source there. So let me just have a copy of this circuit, and then we can simplify it on the next page. Alright, so look now only at the situation corresponding to VB and see if I can simplify the circuit. Okay, I already know what VA is, so I can simplify this circuit in the following way. I'm only looking at this region, right? I'm looking at what I just drew in yellow. So I can simplify this circuit in the following way. I have my current source pointing upward. I have a GMP into VA. Okay, then I have a resistor which is RP. Alright, and then this is connected to another current source pointing down, and the value of that is minus GMN times VD by 2. Alright, and this particular current source then is also connected to ground. Is that right? Okay, and I have this connected to ground here. Alright, and this particular voltage is your VB. Okay, now I'm just going to change something, so be careful as to what I am doing. This is a minus sign and this current is going down, so I'll just flip this. I'll make this current go up, and I'll remove this minus sign. Okay, so I have current going in and current going out there. Alright, and now I want to find out what is the current through this RP branch, and what would that current be? Let me call that as some current I. So the current I will be given as GMN into VD by 2 minus GMP into VA. Alright, and if I have this current, I can find out what VB is as simply this current I going into that resistor RP. Okay, so now can you calculate this? Can you calculate this, please? Okay, so my VB is nothing but GMN into VD by 2 minus of something, and we calculated what VA was on the previous slide. VA itself is this quantity minus GMN into something. So let me just keep all of that here, right? So maybe I'll just copy this here and keep it. Okay. So this was the quantity VA. Okay, so I put that in here. So I'll get plus GMN GMP into VD by 2 whole thing into RP parallel 1 by GMP. That is the current, and the current times RP. Is that right? Okay. Now we can do a simplification. If you realize RP itself is quite large, right, because it's the output impedance of a transistor, and GMP is also going to be large. So 1 by GMP is actually going to be small. So you have a large quantity in parallel with the small quantity. So this entire thing is approximately equal to just 1 by GMP, right? And so then you can cut that GMP with this GMP. So I'll get my final result as GMN into VD by 2 plus GMN VD by 2 and the whole thing into RP, which is nothing but GMN VD RP, which means that the differential mode gain AD, which I'll call as VB divided by VD, is essentially equal to GMN RP. Alright, so this is our first result, that you have a differential mode gain which is proportional to the GM of the NMOS transistor and the output resistance RP of the PMOS transistor, which is the active load. You can include the output resistance of the NMOS transistor also, and that will just change this result slightly. It may become RP parallel RN, but anyway, for us this is sufficient. Okay, so let's keep this in mind. Now let's take the second situation, which is analysis of the common mode incremental picture. So the second thing I want to calculate is the common mode incremental picture, and for that let's have the same circuit that we had earlier. Let me say I will take let's start with this picture and then modify it. All right. Okay, so for the common mode picture, what would I have to change? As I mentioned, for the common mode picture, I want to consider an R0 here. You will see why very soon. Okay, so let me just correct this one first. So just a minute. Okay, so this would be VCM, this would be VCM, correct, minus VCM, and here the current source itself will disappear in the incremental circuit, but I will have an R0 here which is connected to ground. Alright, and this upper transistor M3 can be replaced by 1 by GMP because of the fact that it's effectively a diode connected MOSFET. That is, for this particular transistor, its drain is connected to its gate. Okay, alright. So now this is the common mode incremental circuit, and I want to find out what VB is. Let's start as earlier, and let me find out what VS is first. Okay. So in order to find out what VS is, okay, so I'm going to look at the tail node. What do I have? Again, I have one current entering. That current is GMN into, oh sorry, this is not V, this is, I'm wrong here, sorry. This is VCM minus VS, and this is VCM minus VS, right? Okay, sorry. So I'll have VCM minus VS, that's the current entering here, plus GM into VCM minus VS, that's the current entering this side, and the current which is leaving is going to be V0 by R0. Sorry, not V0, this is VS. Vs by R0. Can you solve this and give me what the value of Vs is? You can show that Vs is actually 2 Gmn R0 divided by 1 plus 2 Gmn R0 into Vcm. Okay, so you see some kind of a feedback which is happening, and clearly in the limit of R0 tends to infinity, Vs becomes equal to Vcm, which is reasonable because these two, if I give in a Vs here and I am looking at the output here, this is essentially like a common drain amplifier, right? So the source will track the gate, and that's what you're seeing here. Okay, so that is the result for Vs. Now what should we next calculate? We should calculate what Va is, all right, and what can Va be? So Va is nothing but, again, it's the current, and the current is Gmn into Vcm minus Vs minus that current into Rp parallel 1 by Gmp. Don't simplify this here, because you will see that if you simplify these things here, you will get very inconsistent results. So just keep it like this, right? And you can put in your Vcm and Vcs and all of that and show that this is right. So just leave this as it is. We'll simplify this later. Okay. Now that is Va. What is Vb? How do you calculate what Vb is? Again, let me have this circuit here, and then we'll calculate what Vb is. So we're not doing anything special, we're just going over things in a systematic way and trying to estimate the various quantities. You can do this on your own, it's not really complicated, okay, but I'm just doing it so that it's all recorded in one place. Okay, and now I'm just going to look at only this region. Okay, and if I were to draw the circuit for Vb, how will the circuit for Vb look? Okay, so I have one current source here. That is going to be Gmp times Va. I have a resistor there which is Rp, that goes to ground, and I have a current source here which is Gmn times Vcm minus Vs, and the only difference being that I have an R0 connected to ground. Okay, again, if I calculate what my current, let me call the current through this as I. What is that current going to be? I itself would be minus Gmp Va, because then that current will flow down, minus Gmn Vcm minus Vs. Okay, nothing very fancy here. We just keep just bookkeeping. All right, and my Vb itself would be equal to I times Rp. Okay, now let me take Va from the previous page, and now let's solve all of these things in one place. I have this here. Okay, now can you simplify all of this and tell me what the answer is? Okay, so we can do it systematically. Vcm minus Vs, you see that this quantity exists here, so this Vcm minus Vs from here will become 1 by 1 plus 2 Gmn R0 into Vcm, right? And which means that your I itself would be minus GMN into show that it is this RP by 1 plus GMP RP, that is this quantity, right? RP parallel 1 by GMP RP, that is this, into 1 by 1 plus 2 GMN R0 into VCM. Correct? Sorry, this is not I, this is VB. Show that this is the case. Very straightforward. You have the value of I here, you have the value of VA, so take this VA, and you have the value of VCM minus VS, put it there, and you have all of this. Alright? And this I can simplify to be equal to minus GMN into 1 by RP plus GMP, right, into 1 by 1 plus 2 GMN R0 into VCM. Now you can do the approximations. So I drop this 1 by RP with respect to GMP, and I drop this 1 with respect to GMN R0, and I will get this as approximately equal to what? VCM divided by minus VCM divided by 2 GMP R0. Right? Alright. So what is the common mode gain then? So I can get my common mode gain ACM as VB divided by VCM is equal to minus 1 by 2 GMP R0. Right? So what can you guess in the in the ideal case of R0 being infinite and GMP being very large? What will happen to this common mode gain? This common mode gain will actually go to 0, and that's why we had this R0 here, because if you took R0 to be infinity, you can't actually calculate the common mode gain. Alright, given the differential mode gain and the common mode gain, which we can just summarize here, you had the differential mode gain AD as being equal to GMN times RP, and you had the common mode gain ACM as being minus 1 by GMP R0. From these two quantities, there is a quantity called the common mode rejection ratio, and that is defined as modulus of AD divided by modulus of ACM. Alright, and this becomes equal to, so there's a 2 here, sorry, 2 GMN GMP RP R0, and you see that all of these quantities are large. GMN GMP RP is large, R0 is large, and this tends to infinity in the ideal case. So what is this common mode rejection ratio, which is otherwise called the CMRR of an opamp? What does it talk about? It essentially says, if I have a signal which has some common mode component and a differential mode component, what is the ratio of the amplification provided to the differential mode component as compared to the common mode component? And you will see that in a differential amplifier, you do not want the common mode component to be amplified, you only want the differential mode component to be amplified. So ACM in the ideal case should be 0 and AD should be as large as possible. So this quantity tends to infinity in the ideal case. Alright. So we have calculated the incremental gain for the common mode signal and the incremental signal. Sorry, we have calculated the incremental gain for the common mode signal and the differential mode signal. The last thing that we need to calculate is the output impedance. Output and input impedances. And this is really simple to calculate. Let's first take the input impedance. Alright. So again, for which circuit do you think I should do this? As you see, the common mode signal is actually attenuated significantly. So I should only worry about the differential mode circuit. So let's go back to the differential mode circuit, and let's just analyze. Let's just take the differential mode circuit and look at the incremental input impedance and the incremental output impedance. So I'm going to take this and have it here. Okay, and if I want the input impedance, what do you think the input impedance is? Right, you go back here. The input impedance for the signal is actually the impedance looking into the MOSFET here and looking into the MOSFET here, because that's where you are giving in the signals. So clearly your Rin is infinite, right? So the input impedance is very straightforward. Let's forget about that. Let's now look at the output impedance. For the output impedance, what should I do? Right, I should kill all my input sources, then energize the output and just see what happens. So I'm going to kill this source. So I short this to ground and this also to ground. Okay, let me do all of that in blue. So I'm going to short this to ground, I'm going to short that to ground. And what should I do? Here I should put a plus minus V test. Look at the current that flows here, call that as I test, and find the ratio of V test to I test. Alright, now the moment that I have connected this to ground, do you see things that happen? Your Vs is anyway at ground, and this was Vd by 2, this is actually Vg, right? This quantity is Vg. So the moment I connect this to ground, this guy disappears, right? So I can remove this source. What happens to this source? This is also 0, so this disappears. Okay, so all of this effectively disappears. Then what happens? What is the current that is flowing in here? That current is 0, which means that what is Vg here or Va, that's essentially going to be 0, right? Why is it going to be 0? Because there's no current flowing in here. This is at 0 potential, so Va is at 0, right? So if Va is at 0, what happens? This particular source disappears because there's no current flowing in here, and then all of this can be removed, and you are left with a very, very, very simple circuit. Okay, all of that goes. So you essentially have the following circuit: V test, I test flows through this Rp and goes to ground. So what do you think your R out should be? Your R out is V test by I test, which is equal to Rp. Alright, so we have calculated the three main quantities of interest: the common mode gain, the differential mode gain, the common mode rejection ratio, and the output impedance of the differential amplifier. This differential amplifier can also be referred to as a single stage op amp, because this is giving you a high gain. However, it has certain problems, and those problems will be looked at in the next lecture, and we'll see that in order to overcome those problems, we have to go to a two-stage op amp. Alright, with that we can close. Thank you.